Hi all, welcome to the second video in our series of videos looking at the hydrosphere. Now in today's video we're going to be looking at different river features, how they're formed, and obviously a little bit of a different surrounding today. I'm recording this from home rather than in my classroom, and an apology that this video has not been up earlier. Now, before we get into our actual river features, the first thing that we need to think about are the processes that are involved in creating any of these features. Now, these are extremely important. Not only do you need to understand where to use the correct terms, but you need to remember that whenever you use one of these terms, or certainly the first time you use one of these terms in an answer, you need to be able to explain what the term actually means. Now, as I say, we've got three main forms of processes. We've got erosional processes, transportational processes, and depositional processes, and they all do very slightly different things. Now, the erosional processes, we've got corrosion, attrition, hydraulic action, and weathering. Now, corrosion and attrition are reasonably similar in that they're quite direct processes that will influence how rocks and pebbles and different material in a river system are actually made smaller. So, and just because I know that it was a big favourite last time, I actually have rocks again. Now, if we've got corrosion, what we're talking about is one rock or multiple rocks that are being pushed by a river, and as they're pushed, they grind against one another. Now, this is where I kind of let you in on the slight difference between corrosion and another phrase you might see mentioned sometimes, which is abrasion. Now, abrasion is any two bits of material that are rubbing, and it's about that friction, whereas corrosion is about things that are rubbing against each other, but they're being moved by something like water or a glacier. And obviously, for our context, we're talking about water moving these. Now, attrition is a little bit simpler in that we've just got any two pieces of material that are floating about, being rolled around in a river, and as that's happening, they bash together. As they continually bash together, they knock little bits off. My carpet in my hall is probably covered in little chips of rock, and that process makes them smaller. Now, moving on to hydraulic action, this is where if we've got small cracks, particularly in the bank of a river, as water flows past it, it forces air into these cracks, and as the air goes in, it goes in under pressure, it makes the cracks bigger. You repeat that process 100, 1,000 more times, that crack will get bigger to the point that it cracks and bits fall off, and that wears away at the riverbed or the river bank. Now, weathering I'm throwing in here is not particularly associated with rivers necessarily, but it is relevant for one of their features. And this is where we've got just the different agents of the weather, be that rainfall or precipitation in general, or changes in temperature. And this causes additional wearing of particularly river banks, and that can lead to some of the features that we're going to be talking about, particularly V-shaped valleys. The next set we've got is how we move material throughout a river system. Now we've got traction, siltation, suspension, and solution. Now, for some of you thinking that solution sometimes appears in erosion as well, it technically can, but we're putting it in transportation for now because that's where it fits a bit more neatly. Now, starting from the top, traction, and I pull out my props again. Traction is where if this is the riverbed and this is a rock that's in the riverbed, it is being pushed along. It's not leaving the riverbed, it's not moving up at all, it's just being pushed along the riverbed. If I've got siltation, I'll have it kind of rolling or possibly bouncing along the riverbed slightly. So the idea is that we do get it leaving the riverbed slightly. Suspension, it is entirely floating along in the riverbed. And solution, you won't see it at all. It's been entirely dissolved down to its kind of mineral component state. And that means that you're not going to see it in the riverbed at all. Now, the last one, when we come to deposition, we're not really talking about a process as such, as we're talking about a difference between the mass of an object and the amount of energy the river has. If the river has enough energy to move a mass, it will not deposit it. If a river lacks the energy to move a mass, or if the mass is heavier than the river's energy, it will deposit it, it will drop it, and it really is that straightforward. Now let's get into our first process, V-shaped valleys. Now, when we look at V-shaped valleys, we think about, and I've got a couple of diagrams here. A point here very quickly. Now, the diagrams that I've got in this video aren't all as schematic as this, but please remember, you are expected to draw diagrams in your answers. However, they don't need to be works of art. The next couple of diagrams I've got coming up for our other features, they are graphics from textbooks, so they are obviously very well produced. You're not expected to reproduce that. Something as schematic as the diagrams I've got here is perfectly acceptable. So sticking with this, first with V-shaped valleys, we are in the upper course of a river, so we are right up in the hills near a river source. And as rivers flow, they erode downwards first. So we call this vertical erosion. Now this happens mainly through corrosion, and again remember, if you're talking about this in your answer, you need to explain what corrosion is. This happens when we cut a deep, steep-sided channel into the valley. Over time, freeze-thaw, which is one of our types of weathering, and this again is what it sounds like actually. It's where if you've got a tiny bit of rock that has got some cracks in it, water gets into the cracks, overnight it freezes, and because the water's turned into a solid, it will expand, and that makes the crack bigger. It thaws overnight, hence freeze thaw, and it then repeats the process, and the crack gets bigger and bigger and bigger until eventually it breaks apart. This and other agents of weathering act on the riverbank, and that loosens the rock and soil that we have there. Now, as the rock and soil is broken up, it's transported by gravity down off the sides of the river into the river channel itself, and then it's transported downstream by the river and it's deposited somewhere else. Doesn't really matter. In this little bit here, I've got it's deposited on its bed or on a river beach, and you can certainly say that, but it's not vital to. The point is, it's transported away, and that leaves us with this very typical steep-sided V-shaped river valley. Next one we're going to look at is waterfalls. Now, straight away, you can see the kind of diagram I'm talking about where this is obviously really high quality. I have pilfered it from Google, but we can see that, yes, it's very, very high quality. You're not expected to reproduce this. You reproduce it, fantastic. You'll make an examiner very happy and give them something nice to look like. But during lessons, we'll look at maybe more schematic representations of this. So, if we think about waterfalls, and I'm going to pull up some of the key points that we've got here, we need alternating layers of hard and soft rock. That soft rock is much, much easier to erode, so we create a step underneath the hard rock. Now, we've got all of the erosional processes are in action here. Corrosion, attrition, hydraulic action, they are all in play, and they should all be explained here, as that makes that step much larger. Beneath that step, we're going to have, or underneath where the soft rock was, we're going to have a plunge pool forming. And again, this is a key term that we should throw in here, that we have a plunge pool that forms, and it's a deep area where the water physically falls into the channel. Now, that bit of hard rock, it sticks out above this plunge pool and it creates an overhang. Now, overhanging things will eventually collapse because it's not supported. So gravity will cause it to collapse. Now that material, because it's collapsed and it's now filled the plunge pool with lots of boulders and pieces of rock, they can be jostled about by the force of the water as it falls in after it, and that makes that plunge pool even deeper. That enhances the erosive power of the river at that particular point. That process continues, it keeps going, and the waterfall basically steps back upstream. And as it does so, we get a steep-sided gorge forming. So you get a valley where you've got two very, very steep sides with a waterfall at the back. And if you look where that valley starts, that's the original position of the waterfall. It's something that if you Google pictures of Niagara Falls, you can see where Niagara Falls has stepped back. And if you go to some of the waterfalls around Arran, equally, you can see that they're in very, very steep-sided valleys and they've stepped back. Another point, and it's just one that's maybe makes plunge pools a bit easier to understand, If you've ever jumped off a waterfall, maybe up Glen Rosa or Glen Sannox, certainly where there's waterfalls you can jump in, that really deep area that you're jumping into, that's a plunge pool. And the reason it's so deep, as we've said earlier, is the erosional processes that are going on are much, much more powerful there because they've got the force of the water as it falls off the edge to aid them. Now, our last features, and it's kind of two for the price of one, is we go for meanders and oxbow lakes. Now, the oxbow lakes, as we're going to discuss, are basically an enhanced version of a meander. We start with meanders, and again, you can see this diagram. It is, it's a proper graphic that I've acquired from the internet. And it is something that if you can create something similar, fantastic. If you can't, don't worry about it. There are more schematic ways to do this, and we can discuss those in class. Now, some of the key points with meanders. Rivers have got areas where they're shallower and where they're deeper. The shallower areas we call riffles, and that results in slower water. The deeper areas we can call pools, and that results in faster water. Now, when you've got areas of shallow water here and deeper water over here, the river starts to whip round these areas, and as that happens, the water starts to turn, it starts to corkscrew, and we call that a helicoidal flow. And again, that's a key term that I would expect people to incorporate into their answers. Now, that faster water, it's got more erosive power than the slower water on the inside, and that starts to make the river move from side to side across the channel. Now, where we've got that slower water on the inside, we start to form something known as a river beach. And the reason we get a river beach here, we go all the way back and we think about what is deposition. The water doesn't have the energy to carry the massive material that it has, so it starts to deposit it on the inside of the bend. And as it deposits on the inside, we form a little beach. On the outside, we start to form a river cliff because the water's very, very powerful and it erodes at that outside bank of the meander. Now, as this happens, the river's going to collapse periodically. The river cliff is going to collapse periodically because it becomes undercut, and that makes the meander even more pronounced. And as this process continues, meanders migrate downstream. Now, just to go back over this a little bit, we need to remember again, where we are talking about, deposition, you can explain very simply by saying that the river doesn't have the energy to transport the mass of sediment, the mass of material that is in its channel, so it drops it. Again, erosionally here, we've got all the erosional processes happening on the outside bend of a meander. So they should all be mentioned: corrosion, attrition, hydraulic action, and they should all be explained. Now, we're going to oxbow lakes. Now, the first bit, and it's a little bit of a cop-out on my part, I'll own up to that, you summarise a meander first. Meanders continue to grow, and the shape becomes more pronounced with this distinctive swan's neck when it's like that. The two outside bends of the neck can grow extremely close. And as that happens, if you get a flood, or when you get a flood, as all rivers flood, the river's going to breach its banks, and occasionally that's going to make those two outside bends, they're going to join. And that creates a new, straighter river channel. And that's going to become the dominant channel because rivers, like all natural things, like to take the easy way out. And if you've got a straight channel downstream, you're going to favour that over a longer, more winding one. So that longer, more winding channel is going to start to evaporate and silt up. That means that the bend is going to become cut off eventually, creating a distinctive oxbow lake. And our last point with this is to remember that it's a temporary feature and it will silt up entirely. Now with this, I just want to bring us back to the diagram here before we finish today, just so we can point out a couple of key bits. Now this here is what I'm talking about with our swan's neck. Now I personally don't see how it looks like a swan's neck, but people insist it does. And you can see here that these two outside bends are getting closer and closer. The river floods, new channel breaks all the way through, and eventually we're left with this oxbow that's left abandoned, and it will eventually silt up. Now this has been a longer video, guys, today. There has been a lot of information in it. We'll obviously spend some time going over this stuff in class, but I'm going to let things wrap up here before I run out of time, and I will speak to you guys on Tuesday. Until then, I'll see you later.